Okay, I'm going to introduce the speaker. First, though, I have the pleasure of announcing that today, Charlie Kane has been elected a fellow of the American Academy of Arts and Sciences. So I think that deserves an extra round of applause. Okay, you probably did hear already.
I did hear, yes. I didn't know that you had heard.
So again, today we have Charlie after yesterday's wonderful lecture. So nowadays, Charlie is primarily known as the main inventor of topological insulators, which he modestly almost didn't mention yesterday. He's also worked on a number of other problems in condensed matter physics, and actually he worked with Doug Stone in early work, and he worked with me. But Charlie wasn't always this impressive giant of condensed matter theory that you see now. In fact, I first met him when he was a young graduate student at MIT. I, of course, was a high school student at the time. And so we actually did work together there. And we also used to socialize and get up to things at the weekend with a bunch of friends. And so there are various stories that I could tell, but I'm not going to tell. There are notable things, including a scientific trip to Brazil, which was organized by Steve Gervin. All right, so with that feeble attempt at embarrassing the speaker, I'm going to hand over to Charlie for today's lecture.
Okay, thank you very much. I mean, of course, I could tell the story about Nick in Brazil. Okay, so thank you very much. And you know, it was fun to be here yesterday. It's also fun to be here today. So I'm really happy to be able to tell you another story. And for those of you who were at my lecture yesterday, the topic is going to be somewhat similar. I want to talk about the interplay between symmetry and topology. And of course, does this work? Just make sure. Why is it not advancing? Good. Yeah. It was working before, and my computer is frozen. Let's see. Let's go. Okay. Maybe I can get that. What do I want to do? Hide the video panel? This one?
No,
oh.
It's hide, yeah, hide meeting.
Okay. Sorry about that. Okay, so look, symmetry and topology are two of the big ideas that sort of underlie our understanding of physics, understanding our way of how matter fits together. And you know, symmetry is a familiar story in physics. You know, it's something that we teach our freshmen about. You know, I teach freshman physics sometimes, and I tell the students that the first thing you think about when you have a physics problem is you understand the symmetries. And that gives you a powerful organizing principle for thinking about the problem, and it simplifies the problem. Now, in the context of you know, phases of matter, the idea of symmetry gives a very powerful organizing principle for distinguishing the phases of matter. Okay, and so if you think of crystalline matter, for example, you know, you have it's sort of like these pictures here, you know, and the symmetries, of course, tell you what operations you can do that keep things the same. Okay, and so you can translate or you can rotate, and it's sort of like this in a crystal as well. And so this is the, you know, an idea that goes all the way back to Landau, that you can classify the phases of matter according to the symmetries that they have or the symmetries that they don't have. Okay, and so this is a very powerful way of thinking about the phases of matter. But there's an equally powerful tool, which is topology. Okay, and what topology is about, it's about what is it that stays the same if you continuously deform something. And as I said yesterday, the classic example of that is the sense in which a donut is the same as a coffee cup. Okay, and so importantly, so topology is able to distinguish phases of matter that have the same symmetry. Okay, and so it's interesting to think about phases of matter that are distinguished topologically. Now, one thing I'll say is that topology in physics is a rather old story. Okay, this is something that goes back many decades, and what is relatively new, what I refer to as the physics of the 21st century, is a new understanding of how symmetry and topology interact with each other. And there's an interplay between them from which you get sort of more than just the sum of the parts. Okay, and in particular, in the context of electronic materials, the interplay between symmetry and topology is very rich. Okay, and so this is what I want to tell you about. And so what I'm gonna do in this talk, and this is frustrating. This is not. Yeah, I don't know why this is doing this. So are we up there? And let's see. Okay, so it seems to work now. Okay. Did I go out of the Zoom? Yeah, I don't know what I'm doing here. Not sure. It's still showing? Okay. Okay, we're good. Oh yeah, good. Okay, good. So, all right. So I apologize for that. So what I'm going to do is I'm going to start off telling you about how topology fits into the band theory of solids. Okay, so that's the context in which topology and symmetry have this great interplay for electronic materials, and so that'll lead me into a discussion of topological insulators in 2 and 3 dimensions. Topological superconductors, which one can understand in a similar way. And then at the end, what I will try to do is I'll try to give you, so this is a field that has sort of blossomed in a huge way over the last, a few decades. And so at the end, what I'll try to do is to give you a little bit of a flavor of where things are at the moment and where things are going in the frontier. Okay, and so to talk about topology and the band theory of solids, I want to sort of start with the most basic state of matter, which is the electrical insulator. And again, an electrical insulator is something that we teach freshmen. I teach my freshmen about when I teach freshman physics. And what I tell them is, in an electrical insulator, the electrons are sort of stuck. They're bound to atoms, and they can't do anything. Okay, and so, but of course, the fact that they're stuck on atoms is a unique consequence of quantum mechanics. Okay, because it's quantum mechanics that tells us the energy levels in an atom are quantized so that there is an energy gap for electrons to do anything. Okay, and so the simplest electronic insulator would be a crystal of inert atoms. Okay, say solid argon. Okay, and maybe that's kind of a boring insulator. Things are more interesting when you have atoms that interact more strongly with each other and form covalent bonds. Okay, and the language that we use to describe the electronic structure of covalently bonded insulators is called the band theory of solids. And this was one of the the huge triumphs of quantum theory in the 20th century. And so basically what happens is that the atomic energy levels in a crystal, they broaden out to form a band, okay? And as long as the occupied orbitals are separated by an energy gap from the empty orbitals, then it remains electrically inert. It remains an electrical insulator, okay? And so the thing I want to say, though, is that there's a sense in which, a more complicated band structure, and covalent insulators can have a rather complicated band structure, okay? And that's something that we understand very well, okay? And so this is band theory, but there's a sense in which these are kind of the same, okay? The same in the sense that you can imagine continuously deforming from one to the other by sort of slowly separating the atoms apart, okay? So actually, there's a sense in which, a covalent insulator is kind of like the vacuum, okay? And of course, the vacuum isn't quite as empty as you might first have thought. So what I was saying, and I again apologize for this delay, is that the vacuum is like an insulator too, okay? If you think in terms of relativistic quantum mechanics, Dirac's quantum mechanics, then electrons have an antiparticle, which is the positron, which is just like a hole in the valence band, okay? And so mathematically, these are really kind of the same, okay? The only difference is that in Dirac's vacuum, the energy gap is 1,000,000 times bigger, okay? So there's a sense in which all of these are kind of the same in the sense of topology, okay? And so I want to elevate this idea to a principle to state that insulators are topologically equivalent if they can be continuously deformed into one another while staying an insulator the whole time, okay? And so the question then that poses for us is whether there are insulators which are different, okay? And I want to describe those insulators, and this is what I talked about yesterday, but I want to describe them on a little bit deeper level, okay? And so we'll start off by talking about in one dimension, we have a one-dimensional polymer, polyacetylene, okay? And polyacetylene is a chain of atoms and a chain of carbon atoms, and there's basically one electron for every carbon atom that's not bonded to the hydrogens. And when you have one electron per site on a one-dimensional chain, then you basically have a half-filled band, which is a metal, okay? But that's an unstable situation because what polyacetylene would rather do is it would rather dimerize, forming strong and weak bonds. And by doing that, what it can do is it can open up an energy gap to make an insulator and sort of lower the energy of all of the occupied electron states. Okay, and so this is called the Peierls instability. And the thing that's interesting about this is that you can do it by, there are two different patterns that you can do the dimerization. Okay, and these two different patterns are topologically distinct in the following sense, which is that, so in this A phase, what I did is I displaced the green atoms to the left, and in the B phase, I displaced them to the right. And you can't get from a positive number to a negative number without going through zero, okay? And when the displacement is zero, then you're back at the electrical conductor. Okay, and so these two insulators are topologically distinct. And so what we'd like to be able to do is to characterize the difference between those two distinct topological states, kind of in the same way that we can distinguish a donut from a coffee cup. Distinguish a donut from a sphere by counting the number of holes. Okay, so can we identify a topological invariant that distinguishes those? And so a simple way of doing that is to consider a simple model Hamiltonian for this one-dimensional chain, which is basically to imagine that you have basically one electronic state on each atom. Okay, and so that means that in each periodic unit cell of this one-dimensional crystal, there are going to be two electronic states. So your Hamiltonian is going to be basically a 2x2 matrix. Okay, and 2x2 matrices are simple that we can kind of understand what's going on. And and in particular, in this 2x2 matrix, the Hamiltonian only connects the blue atoms to the green atoms. So as a 2x2 matrix, it's going to only involve the off-diagonal components, which and you know, one thing you know about 2x2 matrices is that you can always write any 2x2 matrix as a combination of the identity matrix, which is just a constant, that doesn't really do anything, plus some combination of the three Pauli matrices. Okay, and in this case, the Hamiltonian only involves the off-diagonal Pauli matrices, sigma x and sigma y. Okay, and so we can think that what we have is we have a Hamiltonian which is a function of momentum. So you know, so I write it as a function of momentum, and in a crystal, the momentum is defined kind of on a circle. It's called a Brillouin zone. Okay, so we have the momentum on a circle, and so we have a Hamiltonian, which is a function of k, which I can think of as a vector in the xy plane. Okay, which then is a function of k on this circle, and so basically, you know, as a function of k, as you go around the circle, either this vector can sort of go like this, okay, in which case it comes back like that, but an alternative is it could go all the way around. Okay, and so now you can start to see where some topology enters the story, because this Hamiltonian as a function of k can be characterized by a winding number, whether or not it, you know, so here it's sort of doing this, it's not winding around the origin, here it's winding around the origin. So there's a kind of integer topological invariant that we can define, which distinguishes these different classes, topological classes. And in order to go from one to the other, you know, for instance, if I change the sign of u, then in order to get from this to this, I have to go through a point where I go exactly through the origin. And when I go through the origin, that's when the Hamiltonian is 0. That's when it's no longer a insulator. Okay, so in this sense, to go from the A phase to the B phase, we have to go through a topological quantum critical point. Okay, that's the transition between these two. Now, there's a caveat that I want to add to this. So you notice there's a little star here. And you see, because, you know, I told you that we have a Hamiltonian, which is a 2x2 matrix. It's made out of the Pauli matrices. Okay. But then I told you that we're only using sigma x and sigma y. Okay. So you could ask the question, why is that? Okay. Why not use sigma z? Because the thing is, if I use sigma z, then I could get from this to this by just sort of, you know, then there'd have to be another axis coming out of the page. And I could just pull the loop over the top and smoothly go from this to this without going through the origin. Okay. And so it's an essential part of the story that we're not using sigma z. Okay. And so the origin of that is, so this is where symmetry enters the discussion. Okay. So symmetry is an essential part of this argument that these two phases are different. Okay. And so it's interesting to think about what the symmetries that this simple system has. Okay. And there are actually two that are interesting to think about. So one symmetry, which is a little bit of a counterintuitive kind of symmetry, is that if you look at the spectrum as a function of energy in this simple model, the conduction band looks exactly like the valence band. And in fact, there's a reflection symmetry in energy going to minus itself. Okay. And so this symmetry we call, you know, it's called a particle hole symmetry. And it's represented by an operator that anti-commutes with the Hamiltonian. Okay, and if you have an operator that anti-commutes with the Hamiltonian, this sigma z, then if I operate this on the Hamiltonian, then I get minus the Hamiltonian. And so if I have this symmetry that anti-commutes with the Hamiltonian, then that guarantees that for every state at positive energy E, there is a corresponding state, eigenstate, at exactly the minus that energy. Okay, so the eigenstates of this Hamiltonian come in plus E minus E pairs. Okay, and so this is a property of this simple model of polyacetylene. Okay, and I want to argue that this is a useful thing to think about, despite the fact that it is not a property of real polyacetylene. Okay, so this is this particle hole symmetry it's an artificial symmetry. It's a symmetry of a simplified model, cartoon-like model that we write down, but it's not actually in real polyacetylene, there's no sense that there's no zero of energy. Okay, so the zero might be somewhere in between the conduction band and the valence band, but there's no meaning for the energy be exactly zero. Okay, but I want to still argue that this is worthwhile to think about, and you'll see why in the next slide. And moreover, later on in this talk, I'm going to be discussing a related situation where there's a particle hole symmetry like this, which is real and exact and intrinsic. Okay, and so it's worth understanding the consequences of this. Now, for real polyacetylene has other symmetries as well. In particular, it has a you can rotate by 180 degrees about the center of a bond. That's a symmetry. Okay, and it turns out that symmetry is enough to protect the topological distinction between this A phase and the B phase. Okay, so in the presence of this rotation symmetry, or equivalently a reflection symmetry, you can't get from the A phase to the B phase without going through a quantum, without going through a critical point. So now, so given the fact that we have these topological phases, then the natural question is what consequence does that have? And the consequence of this is that on the boundary between distinct topological phases, there are topologically protected boundary modes. Okay, and so this is a problem which has kind of been discovered and rediscovered many times over the years. So let me give you the simplest version of this, which is to imagine that we consider the most extreme limit where the strong bonds are really strong and the weak bonds are equal to zero. Okay, and if the weak bonds are equal to zero, then we just have a bunch of completely decoupled dimers, pairs of atoms that are strongly bonded to each other. So they're going to have sort of bonding and anti-bonding orbitals, if you will, which are separated by a huge energy, and that's going to be the entire story. There's going to be there's going to be a big gap, energy gap between the occupied and empty states. Except if you have a domain wall between the A phase and the B phase, then you can see that there's one site that is sort of left alone. That's not coupled to anything. So it stays at zero. Okay, and so in this extreme limit, then the picture you have is you have a sort of a conduction state, the states at positive energy, the states at negative energy, but then there's a single state that's exactly at zero. Now, so you could say, okay, this is completely artificial situation because I turned off all the weak bonds. So of course it's decoupled. Of course it's still at zero. Okay, but now you can ask the question, what happens if you turn back on the weak bonds? Okay, and so this is a situation where thinking about the particle hole symmetry is a very powerful way of thinking about it. So if we turn back on the weak bonds, but we keep the particle hole symmetry, okay, which we can do. That's what happens in this the simple-minded model, the nearest neighbor model of polyacetylene that we had. Then what's going to happen? So this zero mode can't go anywhere. Because remember, I told you that if you have the particle hole symmetry, then every state has a partner at minus its energy. Now, the state at zero is kind of special because it is its own partner. Okay, so it can't move away from zero. Because if it tried to move away from zero, its partner would have to appear out of nowhere, suddenly, and that can't happen. Okay, So this zero mode is topologically protected. Okay, so we can understand this zero mode, starting from the strong, the extreme strong bonds and zero bonds. We can also understand it from the opposite limit. Okay, and so this is the limit that this phenomenon was first discovered by the field theorists, Jakiv and Rebbe, who were considering basically a one-dimensional field theory where you have Dirac fermions with a Dirac mass that can change sign at a domain wall. Okay, and that is a sort of a continuum description of this kind of domain wall between the A phase and the B phase. It's like having a mass that changes sign. And again, the Hamiltonian, the Dirac Hamiltonian, is a 2x2 matrix. Okay, and one can sort of analyze it in the same way. And for the students in the audience, there is a very nice calculation you can do if you haven't done it before. Which is to show that if you have a Hamiltonian like this with a mass that changes sign, okay, no matter what the shape of this, mass as a function, no matter what the shape of this curve is, there will be an exact zero energy eigenstate that looks like this. Okay, and this is a pretty easy system to solve because the Schrodinger, you basically just solve H psi is equal to 0. And this is a first order differential equation that you can integrate. And you can see that this is an exact solution to this. Okay, so if you haven't done this calculation before, I can assign it as a homework problem. What's that? That's normal. I only care about normalizable states. Yeah. Okay. So now, so we have this zero mode. Okay, and we can understand it, and it exists all the way from the weak bond limit to the strong bond. So this is topological. Now, there's another point I want to make about this, and this is a point that I can make about all the topological states that we're going to be talking about, which is there are two levels that you can think about this phenomenon on. Okay, and one level is to think about it on the level of single particle quantum mechanics. Okay, because that's what we're doing when we solve the solve the Schrodinger equation for a single particle, right? Or when we solve this Hamiltonian, we're solving a single particle problem. Okay, and so when you solve the single particle problem, you get a set of eigenstates with energies and wave functions. Okay, and we discover there happens to be one that has exactly zero energy. Okay, and that has a wave function that's localized on the domain wall. Now, but the thing is, of course, real polyacetylene has lots of electrons. There isn't just one electron. There are lots of electrons. Okay, and the way you think about that is that the many particle ground state, you construct that by filling all of the negative energy states with electrons, occupying them. So the many body ground state has all of these states occupied with electrons, and it has all the states in the valence band are not occupied with electrons. But then there's a choice as to whether or not the zero mode is occupied or not. Okay, and so and again, if we think in terms of the particle hole symmetry, we know that the spectrum is symmetric if we turn it upside down, and so that's sort of like exchanging particles and holes. Okay, and we also know that and so the empty state, if we turn it upside down, will turn into the occupied state for the zero mode. Okay, but we also know that the difference in charge between those states is exactly E, because it's to go from the empty to the occupied, we add exactly one electron. Okay, and so that means so the only number I can think of the only pair of numbers that differ by one and are minus each other is plus a half and minus a half. Okay, And so, so that tells us that the charge on this domain wall, depending on whether this zero mode is occupied or not, is going to be plus or minus a half. Okay, and so this plus or minus a half is our mark. So this is the phenomenon of charge fractionalization. Okay, and so as I said yesterday, there's a sense if I add an extra electron to the A phase, I can split it apart into two charge E over 2s. Okay, and again, one other point I'll make, this is a little bit of an idealization. Real polyacetylene has another thing going on, which is it has electrons that can be either both spin up and spin down. Okay, and so what that means is that actually in real polyacetylene, there's going to be two zero modes, one that could be occupied by a spin up electron and one that could be occupied by a spin down electron. Okay, and so there's sort of two copies of this. So I can either have plus a half a spin up or minus a half a spin up, and plus a half a spin down or minus a half a spin down. So I could have both, I could have a charge E, but it would have no spin, or I could have a charge 0 that would have a spin. Okay, and so so what this charge fractionalization does in real polyacetylene is it changes the relationship between the charge and the spin of the particle. Normally, if you have a spin a half fermion, a charge E goes with a spin of h bar over 2. Okay, whereas here you can have a charge 0 with a spin of h bar over 2 and a charge E with spin 0.
You don't get experiment with which you can see E over 2 charge.
I don't think, not in polyacetylene, I don't think. Yeah. No.
Is it possible in principle?
Well, in principle, if you could have spinless, spin polarized polyacetylene, but that, so no, I don't know of a way to get charge E over 2 in this. But the thing is that this having a spinless charge, having spin-ons and hole-ons, if you will, that's what we could call them, that is just as impossible as having a charge E over 2. Okay, so that's that's true. Okay, so this is a simple version, and we can sort of understand what's going on with this. So my point is there are many more examples of this, and so I want to try to step this up to higher dimensions. Okay, and the logic I'm going to use is going to be very similar to the logic I used in analyzing this this polyacetylene problem. Okay, and so to step it up to another dimension, I want to start by thinking about a one-dimensional electrical conductor. So I can imagine I have a one-dimensional wire. This could be, for instance, it could be the undimerized polyacetylene. Okay, which would be a conductor, and so there, you can think you have some energy as a function of k. Maybe it's k squared over 2m. You fill the states up to the Fermi energy, and then you have low energy excitations near either the right or the left moving Fermi points. So these states, at the Fermi points, they either have a positive group velocity or a negative group velocity. So I can think of wave packets belonging to them either propagating to the right or propagating to the left. And so we gave these states near the Fermi energy, we give them a fancy name. We call them chiral Dirac fermions. Okay, and but the thing about these chiral these electrons in a one-dimensional conductor is that they're very fragile. Okay, in the sense that if there are any impurities around, then electron will be propagating along. It'll bounce into the impurity, it'll bounce back, then bounces another impurity, and it bounces back and forth, and it never gets anywhere. Okay, and so this is the phenomenon of Anderson localization. Okay, and so it's a general problem that a one-dimensional conductor that is disordered, the electronic states will inevitably be localized. Okay, which turns the conductor into an insulator. Okay, so it doesn't conduct electricity. Okay, and a related thing you could do is you could even if you don't have disorder, if you had a weak periodic potential that was commensurate with the electrons, then that would also open up an energy gap, and it would turn the metal into an insulator. This is what happened with the Peierls instability in polyacetylene. Okay, so so the question is there any way that you could keep this from happening? Okay, and so what I want to show you is that there's a way we can split these chiral Dirac fermions apart from each other. Okay, in kind of the same way we did it in polyacetylene. So what I'm going to do is I'm going to imagine, I'm going to start off and imagine that I have a bunch of these one-dimensional wires, and maybe I've turned them into an insulator by putting on a weak periodic potential. Okay, and you know, when I turn on the weak periodic potential, the sort of right-moving chiral fermion is sort of bouncing to the left move, and you know, they're sort of bouncing back and forth between the right and left moving chiral fermions on the same wire. But what I could imagine is that I could imagine having them bounce back and forth on neighboring wires. So if I have the right mover on one wire, then scatters to the left mover on the next wire, and that bounces back and forth, it'll still be localized. It'll still be going back and forth, but it'll be different than what we had before. Okay. In fact, it almost looks a little bit more like cyclotron motion, because the electron in real space is going around in a loop. Okay. And so in fact, if you do that, then you know it's going to be an insulator inside here. The right and left movers sort of kill each other. Okay. And on the outside, it's just what we had before. It's this trivial insulator. But then you can see that on the boundary between the two, there's going to be one chiral mode that gets left behind. Okay, so it's just like what happened in polyacetylene at a domain wall. Okay, and this you know, right-moving chiral fermion is separated spatially from its left-moving counterpart. Okay, and so so this is what a you know, a two-dimensional topological insulator, or a two-dimensional Chern insulator is. Okay, also called a quantum Hall state. Okay, and the quantum and the thing that is remarkable about this quantum Hall state is that it has this edge state, if you will, this boundary mode. Okay, and it's a topologically protected boundary mode, and this boundary mode is remarkable because it's like a one-way street for the electrons. Okay, and if you're an electron, the only thing you can do is just keep going in the same direction. So that means if you put in an electron on one side, you know 100% that it's going to show up on the other side. So the transmission of electrons in these chiral edge states is perfect. Okay. Now again, I want to emphasize that there are two levels that you can think about this phenomenon. So you can think about it on the level of single particle quantum mechanics, okay, which is, you know, so we solve the Schrodinger equation, we get our energy eigenvalues, which are, you know, in the valence band or the conduction band. These states all have wave functions, and then there's going to be a single band of states that connects the conduction band and the valence band. Okay, and these states, you know, they have a positive group velocity. They're the states that form this chiral Dirac fermion. Okay, and of course you can't get rid of these, right? Because you can imagine changing the detailed dispersion of this edge state, but there's no way you can get rid of it because it has to connect the valence band to the conduction. Okay, and so so that's the single particle spectrum. We can also consider, you know, the many body situation. Okay, and of course, in the many body situation, we have to fill all the states up to the Fermi energy, and they give us a ground state, and then that ground state will have low energy excitations, which are like particle hole excitations about the Fermi energy. Okay, and so one can contemplate describing those the many body spectrum as well, and that is something which is well described by a low energy field theory. Okay, and in particular, one could call it a chiral Fermi liquid, if you will. And really, it's the simplest field theory. It's just it's a free Dirac fermion, one plus one dimensional conformal field theory. Okay, and one thing that you can that the field theorists know about this is that it has a problem, which is that it is this theory by itself is poorly defined. Okay, and it's poorly defined because in order to define it, you need to define how it's regularized at infinity, and there's a problem regularizing this. And what the field theorists will say is that the theory has an anomaly. Okay, and there are different kinds of anomalies. There's the chiral anomaly. There's also a gravitational anomaly, and these anomalies are related to the fact that you have these edge states have a quantized electrical conductance, and they also have a quantized thermal conductance. Okay, and these are sort of two separate pieces of information about the sort of many body ground state and low energy excitations of this chiral Fermi liquid. Okay, and so these are two different ways that one can think about this. And now, of course, the quantum Hall effect, has come to life in the real world. The way you get the quantum Hall, the simplest way to get the quantum Hall effect to go is by having a two-dimensional electrons in a magnetic field where the electrons go around in circles, and then that gives you Landau levels, which are basically the quantized circular orbits of electrons, kind of like the motion of electron in an atom is quantized for the same reason cyclotron motion is quantized, and so this gives you the quantized Hall effect, and remarkably, it's incredibly accurately quantized. And I'll say that this is sort of physics that goes back to the 1980s, and it has continued ever since. But one thing I'll say that it's only been within the last few years that in addition to the quantized electrical conductivity conductance, the quantized thermal conductance has been discovered. Okay, and this has been something that has been, it took 20 years after the prediction for this to come about, because it's a much harder experiment. It required some real experimental ingenuity to figure out how to measure the flow of heat. Okay, and but a couple of years ago, Moti Heiblum from the Weizmann Institute figured out an ingenious way of doing that, and measured the quantized Hall conductance, the quantized heat flow that is carried by these edge states. And it's not as good as 1 part in a billion. Okay, it's a much harder experiment, but it is still pretty good. Okay, and this really is an independent measurement. It's measuring something that's really different than what's being measured by this experiment. Okay, and there exist other quantum Hall states where measuring this number is actually a very important thing to do. Okay, and so this is the quantized thermal conductance. Okay, so there's been a lot of recent effort trying to make the similar quantized Hall effect without an external magnetic field. Okay, and this is something where there's actually, in the last several years, there's been a lot of very interesting progress on that. So we call that, we could call that a Chern insulator, is an insulator that is sort of like the quantized Hall effect, but it's in zero external magnetic field, and it's characterized by a topological invariant called the Chern number. Okay, so what I'm not going to focus on that too much. What I want to do is I want to move on, and I want to talk a little bit about time reversal invariant topological superconductors or topological insulators. So the problem is, in order to have this one-way edge state, it is essential that you violate the symmetry under the reversal of the direction of time. Okay, because so let me tell you a little bit about time reversal symmetry. So what time reversal symmetry is about is it is about if you take a motion picture and you run it backwards, does what you observe obey the laws of physics or not? Okay, and so a magnetic field is created by electric currents. So if you run the motion picture backwards, it changes sign. Okay, likewise, the edge state will change sign. It'll change direction. Spin of an electron also changes. Spin is like a angular momentum, and so that will change sign as well. It's actually interesting to think about how that comes about in quantum mechanics. So in quantum mechanics, the action of time reversal symmetry does three things. It flips up spins to down spins. Okay, so that it does. It also gives you this star, which is complex conjugation. And then there's one more thing. It gives you this minus sign, which is my favorite minus sign. So this minus sign is the same minus, it's actually the same minus sign that maybe you've heard if you have a spin a half and you rotate it by 360 degrees, a spin a half will, the wave function will pick up a minus sign. So it's that same minus sign. It's the same, it's also the same minus sign if you have two fermions, which are spin a half particles, and you exchange them. You pick up a minus sign because they're fermions. It's the same minus sign. Okay, so this minus sign has a very important consequence, which is called Kramer's theorem, which is if you do time reversal twice, then it gives you this minus sign. Okay, and what this tells you is that if you have time reversal symmetry, then every state has a partner with exactly the same energy. Okay, so every state has there's a degeneracy called a Kramer's degeneracy. And so this is a fundamental consequence that time reversal symmetry has. And so now I want to ask the question, so there's no way we can have a quantum Hall state or a Chern insulator with time reversal symmetry, because the edge states, they have to know which way to go. Okay, so could there be something if you did have time reversal symmetry? Okay, and so what I want to do in order to think about that is I want to play the same game that I played before of trying to split a one-dimensional wire into two. Okay, but now I want to do it. I want to try to do it without violating time reversal symmetry. Okay, and it's something you can do. So now of course I have to have electrons that have spin up and spin down. Okay, so now in my original one-dimensional wire, I have up spin and down spins propagating this way or this way. And so now you can see how to split it in half. You can split it in half by having on the top edge, you can have the up spins moving to the right and the down spins moving to the left, and the opposite on the bottom edge. Okay, and so what you can see from this is that this is going to look the same if you run the motion picture backwards, right? Because the right mover will turn into the left mover, but the up spins will also turn into the down spins. Okay, so this is a topological state that is compatible with time reversal symmetry, and in fact, it is protected by time reversal symmetry. It'll have similar edge states, so these states, there are states moving in both directions. So the up spins are moving to the right, the down spins are moving to the left, and you can see they cross each other here. Okay, and usually in quantum mechanics, when you have states that cross and have a degeneracy, there better be a good reason for that degeneracy, because otherwise any small perturbation would turn the crossing into an anti-crossing. Okay, but this crossing here this degeneracy here is precisely a Kramer's degeneracy, which cannot be lifted by any time reversal invariant perturbation. Okay, so these states are protected by time reversal symmetry, and these states also have an anomaly. Okay, it's a Z2 anomaly. They have a topological invariant like the Chern number, but now it's a Z2 topological invariant that only has two values. Okay, And now, in order to get this to go, okay, it's compatible with time reversal symmetry, but we do have to have some interaction of the spins. Okay, so a necessary ingredient is that you have a spin-orbit interaction. And actually, the best place to make this, to find this happen is in materials that have a very strong spin-orbit interaction. Am I already out of time, Nick? Okay, good. Okay, but I'm getting close. Yeah.
Well, we're going to give you more time because
Okay, but I will not go too far. I don't want to keep everybody too long. So so let me just say, so this, you know, this sort of came to life in the real world, and this was a very, very important advance in these mercury cadmium telluride quantum well structures. Is sort of a two-dimensional sandwich structure, which is made out of materials that have very strong spin-orbit interaction. At the bottom of the periodic table. Okay, so so let me say, so one can do the same thing with the three-dimensional topological insulator. I'm just going to go through this very fast, and we can imagine playing the same game of starting with a two-dimensional electrical conductor and splitting it in half. Okay, and then what one has on the top and the bottom surface are you know, sort of states that have a kind of a single Dirac cone in their electronic structure, and this is what happens in that case. So let me, I want to tell you a little bit about one other topological state, which is a topological superconductor. Okay, and you know, you might say that a superconductor is, you know, that's as far away from an insulator as you could get. Okay, a superconductor is not an insulator. Okay, but the way that we understand the electronic structure of superconductors is very similar to the way we understand the electronic structure of insulators. Okay, and in particular, if you think of, you know, so a superconductor requires interactions between the electrons. Okay, but if you take the point of view of the mean field theory that Bardeen, Cooper, and Schrieffer introduced. So if you think about the BCS mean field theory, then one replaces the interacting problem that has some interaction between the fermions with an effective single particle quantum mechanics problem. Okay, and that single particle quantum mechanics problem has a spectrum of energy eigenvalues and eigenvectors, and it has an energy gap with the same structure that an insulator does. Okay, now the price that you have to pay in order to have this sort of kind of semiconductor-like picture for a superconductor is that you have to sort of double the Hilbert space. So you can write your Hamiltonian as a 2x2 matrix. So I have my Hamiltonian and minus my Hamiltonian, and then the off diagonal terms sort of couple, give you the psi dagger terms. Okay, and so when you do this, this Hamiltonian has an intrinsic particle hole symmetry. Okay, so remember when I told you about the polyacetylene, I gave you this fake particle hole symmetry. So this time it's real. Okay, and in particular, there's an operator that anti-commutes with the Hamiltonian, and you know, in addition to giving you this intrinsic particle hole symmetry, there's also an intrinsic redundancy that is built into this description. Okay, because you know, so for every state at positive energy, there's a corresponding state at minus energy that has exactly the same, you know, minus that energy. But if I think about the operator that adds an electron into that state, that is exactly the same operator as the operator that removes a particle from the negative energy state. Okay, so those two states at energy plus E and minus E, they're really just sort of redundant copies of the same state. Okay, so that is the price that you pay for this single particle picture of a superconductor. But now you can ask the question, you know, so we have an energy gap and we have some, you know, Hamiltonian as a function of K. Could it have topological states? And so the simplest version of that is what happens in one dimension, and it's really just like the Schrieffer-Heeger model, you know, this polyacetylene model that we wrote down. So you could ask the question, you know, if I have a one-dimensional superconductor, could there be bound states bound at the end. There's going to be sort of states at positive energy, states at negative energy, separated by an energy gap in the bulk. Could there be states within that energy gap that are localized at the end? And now, of course, we know that if there's a state at positive energy, it has to have a partner at negative energy. Okay, but a state at zero energy could be its own partner. And if you have a state at zero energy that is its own partner, you can't get rid of it, right? Because it can't move away from zero because its partner would have to appear out of nowhere. Okay, so these states are the kind of magical Majorana zero modes. Okay, and the thing that is magical about this is that, I told you about this redundancy. So adding an electron into a Majorana zero mode does exactly the same thing as removing an electron. Okay, so you could ask the question, how could that possibly be? Adding an electron can't be the same as removing an electron. The reason that it can be the same is because you have to think about what a superconductor is. A superconductor is a condensate of Cooper pairs, of pairs of electrons. So pairs of electrons are bosons, and they can condense. Okay, so in a superconductor, you can give away a pair of electrons for free. Okay, so removing an electron is like adding an electron and giving away a Cooper pair for free. Okay, so that's the reason that can happen. Okay, and so there's a beautiful idea that if you could have these Majorana modes, then two Majorana modes kind of define a single Dirac fermion mode, which defines a two-state Hilbert space. Okay, so if you have a topological superconductor with two ends, then the ground state of that is actually twofold degenerate. Okay, and the two states there, in a sense, can form a qubit. Okay, and so this is this idea, beautiful idea of Kitaev's, that these Majorana modes might have some application for quantum information. Okay, so this is all I think I'm going to say about topological superconductor. I think I'm going to skip through this, but I want to give you some flavor of where one can go with all of this stuff. Okay, and there are sort of two directions that one can go in with these topological states, and they're basically based on the single particle and the many particle interpretations that I gave you. Okay, so you see, because the single particle version of topological states can apply to any wave phenomenon. Okay, any wave, it's basically the Schrodinger equation is a wave equation, and when you solve the eigenvalues and eigenvectors of that, and those can have topological states, and for that there's many versions of the interplay between symmetry and topology. Okay, and for example, crystal symmetries have a huge interplay. And let me just say that so for example, graphene. So graphene is a material. It has these Dirac points, and you can ask the question, why do you have these Dirac points? And the answer to that is because of the interplay between symmetry and topology. And there's an interesting thing. So graphene has Dirac points. It has 4 of them. Okay, because there's 2 spins and there's 2 valleys. Okay, you could ask a question, and you could ask a question: is it possible to have fewer Dirac points? Okay, now one thing I told you is that to have a single Dirac point when you have time reversal symmetry is impossible unless you're on the surface of a topological insulator. Okay, so you could ask that, what's the next best thing? Could you have 2? Okay, and it turns out that it is impossible to have 2 Dirac points in a 2-dimensional system that are protected by crystal symmetry. Okay, so that invites you to ask, well, could I have that on the surface of something? Okay, and so that defines another level of a kind of topological state. You could imagine there's some three-dimensional material that has this forbidden single pair of Dirac points on its surface. Okay, and so that's an example of this interplay between symmetry and topology, and this is something which could play out, in electronic materials. It could also play out in photonic materials, elastic materials, mechanical. So quantum mechanics isn't necessarily an essential ingredient in this. Okay, so my final thing is that when you bring in the many particle version of what I was talking about, okay, that we're really talking, in electronic materials, we're really talking about many particle electronic states, and there is a much richer realm of possibilities that can happen. And so let me just give you one example of that. So I told you that what the quantum Hall effect essentially allows you to do is take a one-dimensional wire which has right, left, and left moving chiral Dirac fermion modes, and allows you to split them. So you have the right mover over here, the left mover over here. Okay, so you can ask the question, can you split that any further? Okay, and if you have a superconductor, I told you that a superconductor kind of splits a Dirac fermion into two Majorana fermions. Okay, and so if you have a two-dimensional topological superconductor, then that splits the chiral edge state, which I will say has C = 1, into two chiral Majorana edge states, which each have C = 1/2. Okay, and so now this is actually not a completely stupid idea. Okay, this is something which I feel like should work in the real world. Okay, and there are people who have said they have done this. Okay, but it's not. It's still a controversial subject. Okay, so there's people are fighting about this, and so I don't want to say that this has been accomplished yet, but I think I would like to say that it should be able to be accomplished. Okay, and there are good reasons for wanting to try to do this. Okay, now, but you could say, well, could we split it any further? Okay, is that the end of the line? Okay, and what I'd like to argue to you is that, well, so if you just have one chiral Majorana fermion, I don't know how to split that. Okay, but if you give me 7 of them, then at least in principle, I know how to split. Now this I think, humor me here. So this is less in the realm of what I think is going to come to life, at least in the short term. Okay, but as a matter of principle, if you have 7 copies of these chiral Majorana fermions, then they can split in a rather interesting way. Okay, so it turns out that 7/2 is equal to 7/10 plus 14/5. Okay, and 7/10 is a number which is related to the tricritical Ising model, and 14/5 is related to another theory which is called G2 level 1. Okay, and so these are rather interesting conformal field theories, and there's a sense in which 7 chiral Majorana fermions factorizes into a product of these two conformal field theories. And what that means is that a Majorana fermion incident in here can split into a pair of Fibonacci anyons. Okay, and Fibonacci anyons are something we would dearly love to be able to create in the world. So I don't know if this is the best way. Maybe the best way is to use Nick Reed's, state. But this is something that it would be wonderful to be able to do. Okay, and I think now the thing is that this is a situation where theory is way ahead of experiment. Okay, and so there's a lot of understanding about these kinds of models, but I think much more needs to be done in order to translate this into something where you can actually imagine a real physical system that does this. Okay, so at this point, it's still a matter of principle rather than a matter of practice. Okay, so I want to finish up, and again, I went way over, so I think I'll just put this up there and say thank you very much for sticking around.
Okay, great. Thanks for that beautiful talk. Other questions? Steve?
The trick that lattice gauge numerical simulator same as moving your two direct codes to opposite.
Yeah.
The space-time boundary or something.
Yeah, no, exactly. Yeah, that's right. Yeah, that's right. So, right. So they knew about that. Yeah, that's right.
Charles?
Hi, thanks for the talk. So I wanted to extrapolate what you said about the topological quantum computer point in the SS
Yes.
model to direct.
So the Dirac point in graphene, that's also a topological quantum critical
Well,
point.
yeah,
And what topological boundaries or regions does it separate?
well, okay, right. So it's certainly a critical point. It's not an insulator, and so there are various ways that you can open up an energy gap in graphene, and you see there's a lot of freedom because there are actually there are four Dirac points, right? Because there's two spins and there's two valleys, and so you could put masses on those with different signs, and those all correspond to different topological gapped phases. Some of them will be just trivial insulators. Some of them will be quantum anomalous Hall insulators, so they'll be Chern insulators, and they could be a quantum spin Hall insulator, a two-dimensional time reversal invariant topological insulator. So in fact, back almost 20 years ago, it was precisely this logic that I followed, which led me to the idea of the two-dimensional topological insulators. I was interested in graphene. That's what I was interested in thinking about. And I asked the question, what are all the possible mass terms I can write down in graphene? What are all the possible ways I can open up an energy gap? And so the Dirac point that you're talking about is a critical point that separates all those different phases. And so what I realized at the time was that there exists a mass term which is consistent with time reversal symmetry, and is consistent with all of the symmetries that graphene has, that opens up an energy gap. Okay, so I concluded that graphene has an energy gap, which of course we all know it doesn't. The reason that it doesn't is because the term that I wrote down relied on the spin-orbit interaction, which is incredibly puny in graphene. Okay, but it's not zero, and that was that not zero thing was the the thing that kept me going for a while, until it was discovered that the same thing happens in materials that do have strong spin-orbit interactions. So yeah, so I sort of went off on a tangent there, but a very nice question.
Other questions? Yep.
Yes, I have a question about the obvious again.
Yeah, sure.
If you sort of squint at all these kind of devices, place the CH, but if you try nitrogen, add this poly nitrogen, you definitely have like a topological face full of glass shards. But if you had phosphorus, I think there are certain allotropes of phosphorus that could have a chain-like structure, and I'm just wondering if anyone's looked into that.
Well, certainly, I mean, certainly there's a huge literature on the electronic structure of those sorts of polymers, and then they behave in different ways. So I'm not sure I can say anything general about that, but certainly, you know, that's a very, you know, this is a very well-studied problem. Yeah,
Okay, is it okay if I ask one more question?
it's okay with me.
Make it quick.
Okay. You could flip the A phase of the polyacetylene to get the B phase, but so I guess in a sense they're kind of the same, but is that fine because doing that preserves the boundary modes?
Yeah. So are you saying that the A phase and the B phase, you know, they look exactly the same because I can just sort of do this and they turn into each other?
Yes.
That's true. So you have to define yourself what the rules of, you know, so when I say that you can't get from one to the other smoothly, you have to define what the rules of doing. So what I do, when I'm saying that, I'm saying I want to just move the atoms a little smoothly. I don't want to take an atom here and then flip it all the way over to here. So one has to define the rules of a smooth deformation.
Thank you so much.
All right, since it's getting late, I think I'm gonna cut off the questions here. Sorry, you. No, sorry, too slow. No, I think we're gonna have to, let's thank Charlie again.
I wonder when people get stuff.